Mediterranean. Look at the differences between east of India and west of India. In some cases you can see low salinity coming out of areas where you've got rivers with plumes. So there's a lot of things that you learn by this. And again, this theme of Earth system science, when you start combining salinity data with precipitation data, with temperature data, with sea surface altimeter data, you can really start putting the pieces together and saying, now we're in the position to really do some quantitative science and to really think about initialization of the models and testing of the models, because if people are going to be using climate models to look at the future, we've got a responsibility to make them as rigorous as we can. And quantitative use of the models the use of the models for quantitative evaluation is something that we really can do. Next. Going to look at the Arctic. And this shows the annual Arctic sea ice. You tend to get a minimum in sea ice extent in the September time frame, and this uses 35 years of passive microwave data from a variety of providers. Most of that's not ours. You can see a downward trend, but it bounces down, and in the background you get a sense of the geographical distribution of the sea ice at the end of this minimum period. And you see it's going down, it bounces around, 2007 drops, begins to come back up, 2012 drops down, 2013, 2014 back down. It's one of the common themes in what you'll see in this is that nature does not give us, or a combination of us and nature does not give us many monotonic curves, and it also tends to give us some spatially variable kinds of things. If you look a little bit more here, not at the line, but look at where the ice edge is at the end of the summer, you can see that, especially by the time you get to the end where it's dropped a lot, those are some real changes, that parts of the Arctic Ocean that always have ice at the minimum period don't have ice right at the end. You can look at some areas, and areas that would have been covered in ice normally are not. We're not quite at the Northwest Passage stage yet, but certainly when you think about it, assuming that there are going to be people who probably look at it and say, well, what does this mean for shipping? Will we be able to navigate in places and times that we never could before? For some, that's an opportunity. For some, that's a challenge. In this business, opportunity and challenge do tend to come together. Next shows something else that we can do. I mentioned the GRACE satellites that use gravity measurements. So this is looking at the ice mass change in Greenland over a period of time, because it measures variations in gravity. Well, in some sense, the mass of Greenland as an island isn't changing. What's changing is the amount of ice on Greenland. And you can get some sense, sort of at the seasonal basis and spatial fairly low resolution. You see it's going down steadily, but there's a seasonal cycle. But where you are getting decreases, it tends to be around the edges. You're actually getting increases in ice mass in the middle. And again, if it weren't for satellites, I don't know how you could even begin to contemplate, posing the question, how's the ice mass changing on Greenland? But this is rigorous. This is a great way to do that, and especially when you see that the changes are taking place most rapidly at the edges. That's the ocean ice interface. That's a really active area of physics and research. So one of the things that we have going now, it's an airborne, actually a joint airborne shipborne campaign, normally called OMG, for oceans melting in Greenland, to drop sort of vertical probes into the ocean to get some sense as to the vertical structure of the temperature around the coast of Greenland. Because if we want to understand what's going on, we got to really build up knowledge, and because the rate in which the ice sheets are melting, and if that melting is occurring at the ocean ice interface where we're seeing it, the rate of ice melting is what's going to help influence in a significant way the rate of sea level rise. So these are the kinds of things that we're doing with the GRACE satellites, and I'll tell you a little bit more about them later. Next. This is doing something else that GRACE does, because I mentioned it can measure the mass of ice. It can also get the mass of groundwater. So this represents more than a dozen years of groundwater in California. You're not getting it, terribly high resolution temporally, but you're getting some seasonal impacts, you're getting some spatial impacts, and you can see the groundwater withdrawal. Again, it's not monotonic, because of the years when you get more rain, you'll get some replenishing of the groundwater, but other times it goes down, and this one stops 2013, so we haven't gotten to some of the more recent drought. And I'm showing this for California. We've done this for the central part of the US, but we've also done this for Northwest India and Pakistan. Got some interesting press out of that. We've done that for some areas of the Middle East. And groundwater data can be hard to get some places, so the fact that these are cases where it's really telling, and it's a way of reminding ourselves, say in some cases, if the utilization of water, for good purposes like feeding people, is outstripping the water that's coming back in. What does that mean about the future? At least it's a quantitative way of telling us that we've got a challenge to face, but it's always better to face a challenge with good solid information than it is to do it on the basis of speculation or just assumption that the future will be like the past, which we know it won't be. Next. Getting ready to wrap up here. This is a new view of the Earth. Earlier this year, there was a satellite called Discover, launched as a partnership of NOAA, the U.S. Air Force, and NASA. It's primarily a space weather satellite. It sits at the L1 Lagrange point, about 1 million miles out from the Earth. But you got the space weather instrument on one side, and you got Earth viewing instruments on the other, including one that's like a 12-channel camera called EPIC. So what you're getting to see here is a transit of the moon in front of the Earth. Right now, sort of, you can get the basic pictures about every 2 hours. You get one of these EPIC images, and you can actually go online and get them because at the Lagrange point, the Earth is turning. It's not like the geostationary satellite, where the satellite moves with the Earth and you're always looking at the same part of the Earth. This, over the course of the day, you're always looking at the sunlit Earth, and it's a great way to look up to the poles. And in the future, as the scientists beat on the algorithms a little bit, we should be able to get some quantitative information about ozone and maybe some other constituents there. But in the meantime, you get the picture of the Earth, but the picture of the moon is, I just think that's so cool. If you pick up one of the calendars that we'll put out when the talk is done, assume we still got some more. I think that's June in the calendar. And July is Pluto for the New Horizons image too, so the calendar's great. Next. And this is my last chart, is to show you a little bit about what we're going to be doing in the future. Because the hope is that, if you come back here next year or 2 years from now, whenever, we'll have new things to show you, not just from new things that we're learning from the satellites that we've got, but from some of the satellites that we'll be doing in the future. So I wanted to talk about a couple of the ones that we're going to be launching in the future. I mentioned the International Space Station becoming a big platform for Earth viewing. Next year, we should have 2 payloads going to the International Space Station. SAGE-3 to study vertical profiles of ozone, aerosols, water vapor, and NO2. You say SAGE-3, it's actually the 4th SAGE instrument, because this will be the 2nd SAGE-3. SAGE-1 flew in, I think, late 70s, SAGE into early 80s. SAGE-3 flew from mid-80s into the early part of this century. SAGE-3 flew for a couple of years around the turn of the century on the Russian satellite. This will go on ISS. It's a great orbit for that. LISS is a lightning imaging sensor. It's basically about as close to a copy as you can get of the lightning imaging sensor that flew on the TRIM satellite from 1997 to 2015. TRIM was in the 35-degree orbit. This is in the 51-degree orbit. So we'll get some different information and the spatial coverage of lightning at some mid-latitudes, and let's look at some of the continental lightning that we couldn't look at before. Cygnus will be a constellation of 8 nanosatellites that will be launched towards the end of 2016. It's the first one from our Earth Venture program, designed to look at the winds associated with tropical cyclones. So, because in some cases, if you want to really be able to watch the Earth evolve, there's 2 ways to do it. You go further out from the Earth, so you can sort of see the Earth, as things evolve. Normally in low Earth orbit, you're going around, as I said, the 7 kilometers a second. By the time you get back to where you were, the Earth is turned. So you're not actually watching any one part of the Earth evolve. You have to kind of piece it together. But if you go further out, you can stare. Or if you have enough satellites, then you can just sample every couple of hours and build it up that way. So that's what Cygnus is going to try and do for the winds associated with tropical cyclones. 2017, we'll launch a GRACE follow-on. The original GRACE has been flying since 2002. Batteries are getting a little testy there, so it's good to have a follow-on if you want to be able to keep the data record up. 2018, ISAT-2, we had a ISAT-1 for a number of years, and when that failed, we started doing a bunch of airborne campaigns to try to provide some of the same coverage. It's for ice sheet thickness is the primary thing, but we can look at sea ice freeboard. We can also look at some elements of vegetation canopy structure over the land. So this will be a new improved one that will have multiple lasers. It'll give you information to look at sort of, highly sloping areas, whereas the original ISAT was just kind of one laser. Some more payloads for International Space Station, the LiDAR for looking at vegetation, the passive sensor for looking at vegetation's use of weather. SWAT, another one, a long series of partnership with the French on sea surface altimetry, but it's higher resolution, so it will do coastal altimetry and also do inland water, so you do river stage, lake height. Tempo, it'll be for studying air pollution, ozone, aerosols. It's going to be a hosted payload on a commercial geostationary satellite. Instruments being built. We don't actually know what satellite it's going to fly on, so this is new for us as a hosted payload. Though we say no later than 2023, if the timing works out, Korea will have a very similar satellite launched. The Europeans will have a similar satellite launched. So we'll have a global constellation of really being able to look at air pollution in that time frame. NISARS is a synthetic aperture radar that will be a partnership with the Indian Space Research Organization. That'll be launched in 2020 or so. It's an L-band radar. India's going to provide the S-band radar that has applications for a variety of disciplines: terrestrial ecology, terrestrial hydrology, cryospheric science, Earth surface and interior, and a lot of applications looking at land surface change. PACE is a satellite for studying the oceans, a high spectral resolution to really look at not just sort of phytoplankton, but different kinds of ocean biology, and really give us a sense, and look very carefully also at the overlying atmosphere, because when you do those kinds of measurements, 10% of your signal's the ocean, 90% is the atmosphere. You got to get the atmosphere right to get the ocean right, and you want to learn a lot more about the biology, the sources of biology in the ocean. EVM2 and EVI3 we don't know what they are yet because they haven't been selected. Proposals for EVI3, so Earth Venture instruments, those are being evaluated, and proposals for Earth Venture missions are due soon. So this is the cases where the research community gets to, we don't tell them what to do. They get to decide, they get to propose, and then in the end we have to pick. So it's a way of really tapping into the creativity of the community, and for us the community, it could be academia, it could be NASA centers, it could be industry, any combination of them. So we don't know what it'll be, but it'll be good, it'll be exciting, and the hope is that some years in the future I'll be able to tell you all the good stuff that's coming out on that. In closing, a couple of things I want to say. All the imagery is available. We've got little booklets there that describe it, how to get it. The Scientific Visualization Studio at the Goddard Space Flight Center really is responsible for most everything that you'll see. We've got some calendars that have the imagery. Help yourself. I want to acknowledge Eric Sokolowski, who sits there quietly. He's really one of the architects of the system, or maybe the major architect of the system. He makes it run. He gets to sit there and deal with all the computer problems. I get to stand up here and have the fun of talking, and so I want to acknowledge Eric. If you're here next week, we'll have tomorrow Michelle Burek from the Jet Propulsion Laboratory will be doing 3 narrations, and then next week we'll have a new team, Patrick Taylor from the Langley Research Center, and Stephen Clausen from the Global Modeling and Assimilation Office at the Goddard Space Flight Center. So you know, come back different times, give you different things. Then I'm happy to take a few questions, and there's also posters. So if you like the night lights, you can grab a poster. Yeah.